My name is Kenny Haas, and I am a wind turbine operations engineer with Orsted. So I'm focused on our Northeast portfolio, which involves South Fork Wind, which recently just completed construction and is now operational. And then I also oversee Block Island Wind Farm. So for the presentation today, I'm going to give you some background about myself and then just a quick overview of an offshore wind farm, which we've kind of gotten into already. But then I really just want to focus on showing you some pictures from inside of the turbine that maybe you haven't had a chance to see before, and then really getting into how you get involved in the industry, where some of the opportunities are. So I was born and raised right here in Stony, Brook, New York. I'm very happy and proud to be a local stakeholder working on offshore wind here. And I graduated from RIT in 2020 with my bachelor's and master's of science in mechanical engineering. I started my career in wind down in Charleston, South Carolina at Clemson University's wind turbine drivetrain test facility. I then worked at a company called Energy, focused on onshore wind as an operations engineer for about 2 years. And then I came over to Orsted and now focused on offshore wind, also as an operations engineer. Fun fact about me, I love to snowboard, and in college I was on the freestyle snowboard team. And just to give you an idea of what an operations engineer is, that basically means you're an engineer once the project is already up and running and now operational, and you're dealing with the working asset. So a lot of my day-to-day is just focused on optimizing the turbine performance, make sure we're getting as many green electrons onto the grid as we can. So that might involve being the first line of technical troubleshooting support. If a technician calls you at a tower and says, hey, you're seeing this issue, having a hard time solving it, proactively trying to find issues, maybe something trending the wrong way before it actually becomes a fault and leads to downtime, or when you do have the case of a failure or a fault, performing root cause analysis to figure out what went wrong and how can we prevent that from happening in the future. And then we kind of went through this before, but I'll mainly be talking and highlighting on the wind turbine generators, but okay. Maybe focused on the wind turbine generators, but I did just want to mention that there is a lot more technology outside of that, the offshore substation, the underground cables, and also your interconnection facilities, all very complex engineering that goes into that as well, and I'd argue maybe even more complicated than the turbines themselves. But before we talk about offshore, I did want to just briefly talk about onshore, because I think it helps set the kind of stage for the type of turbines that we're dealing with here. So this is a picture of a 1.5 megawatt GE turbine. It has a 77-meter rotor. This is something very typical that you would have seen built in the early to mid-2000s. I've climbed these turbines many times, and kind of the platform that you walk in the nacelle, which is that back area, is about halfway up. I can't even stand up straight in it without hitting my head. That's just kind of the scale we're talking about. And again, 15 years ago, this is what you would have been building onshore. When we talk about offshore, the scale of things are quite different. There's many reasons for that, but we've got another person kind of standing there for scale. To give you an idea here, the nacelle, again, that back portion, is 4 stories tall. And then the rotor diameter, when all the blades are on, is 200 meters. So we're talking about a 3 times larger rotor diameter. And then the max power output of our turbines, which are 11 megawatt Siemens, is 10 times the max output of those onshore turbines you saw previously. And this has been a direction that the field has been going in for a while, but I'll kind of talk about at the end why this is also a reason why there's so many opportunities right now for engineers joining. So now I'm just going to show you some pictures from the turbine. This is one of my colleagues standing underneath one of the nacelles before it got shipped over here from Europe. But again, just to kind of give you an idea of size and also where he is. So if I actually go back to this slide, so to give you the lay of the land, I'm going to kind of go from back to the front in some of these pictures. Again, that back area is the nacelle. That next area, the cylindrical part, is then your generator, which is your permanent magnet generator. That's where the electricity is made. And then you have your front section, that's your hub with blades that you connect into. That's your rotating assembly part of the turbine. So this picture over here on the left is basically showing you the perspective from if you were standing in the nacelle and you were in the back left corner, you're looking towards the blades. And the lay of the land here is that you're basically on like kind of the middle floor of the turbine here. If you go up those stairs, you're then going to be standing on the roof, and then that's where you would be heli hoisted in. That's the way you're getting to turbine by a helicopter, and then you can also go down, and then you would be kind of at the bottom floor of the turbine when you're then on your yacht deck. And then the picture on the right is just showing you a picture kind of taken from if you were standing on those stairs. And if you look in the right of that picture, you can kind of see that lower floor with the yacht deck, which I'll talk about a little more. And then the two kind of large electrical cabinets that you see, those are the converters for the turbine themselves. So that's what's actually eventually converting the power to your nice 60 hertz AC, and it's ultimately connecting to the grid, providing that renewable energy. Then if I click ahead one more, so this picture on the left is just showing you now a perspective you're standing in the front of the cell looking towards the back, but mainly focused on the hydraulic crane here. Every turbine inside of them has its own hydraulic crane. In offshore, this is very critical offshore because the logistics of doing things are much harder. If you're doing a maintenance activity or troubleshooting, you need to have the ability to do heavy lifting when you're right there. And then on the right, this is now showing you a picture if you were standing inside of the generator, but you're looking towards the back of the turbine. And basically that little opening that you see in the back there, that's directly underneath where the crane is. And those cabinets that you see on the right and left, those are basically the control cabinets for your whole turbine. I didn't have any pictures from the inside of them, but they're really actually not that cool when you see inside. It's just a bunch of wires, different like PLCs and controllers and whatnot. That's what's really just the brains of the turbines doing all the controls. And then you can see in kind of the bottom left of that picture, that's actually your hydraulic power unit. So that has 3 motors on it, and that's what's actually giving you your pressure for your hydraulic systems. So that's going to power your hydraulic crane that you see there, your yaw system, which basically points you into the wind. If you need a brake to stay in the same position, it'll power that. And then it'll also power your pitch system, which I'm showing you here. So now if we go from standing in the generator looking towards the back, and we turn around looking towards the blades, now you're standing inside of the hub, and this is something that you could expect to see as well. So over on the right, that is your hydraulic manifold. So this basically has different manifolds, a lot of valves in them, and actuators that control where the fluid is going to achieve your desired pitch operation, pitching towards power or away. And then over on the left, that's showing you some pictures of the hydraulic rams themselves. That's actually how the pitching is done in the turbines when you're using a hydraulic system. And then finally, on the left over here, this is a picture from the bottom part of the turbine. So if you were standing down there on that bottom yaw deck, this is showing you 6 of the 12 yaw motors. The whole nacelle essentially just sits on top of one large bearing. That bearing's geared on the outside, and then the pinions from all of these motors mesh with those gears. That's how you're actually able to turn the turbine in and out of the wind. And then finally, over here on the right, this is just showing you a picture of the converters. Honestly, not the coolest piece of technology to look at, but probably arguably the most important one in the turbine. That's because this is taking the AC power that your generator is making, it is converting it to DC and rectifying it, and then converting it back to AC. The reason why this is so important, and it's kind of the magical part of the turbine, is it's taking your AC energy that your generator is making, which is not a set frequency and will change with your wind speeds, and then the AC it's putting out on the other side is always going to be a nice sinusoidal 60 hertz. That way you can actually connect to the grid. A lot of fancy electrical engineering that goes in there that I won't get too much into. But then I really wanted to get into the opportunities for offshore wind on Long Island and the Northeast in general. Just kind of talk about why it's being built now and why it's here to stay. So over on the left, you can see one major aspect is that there's a lot of electricity demand in this area. The Northeast is one of the most densely populated places in the US. We also have some of the highest per capita energy usage, and there's a lot of load centers right in this area. It corresponds almost perfectly with the wind resources though. And offshore in general, we have some of the best wind resources in the world, so having that resource located directly with the load, something relatively rare, something we're very lucky to have here. And then finally, some of the other presenters have talked about, there's a very large continental shelf here, which means you have the ability to actually use monopiles. You don't need to try and use more experimental technologies like floating. You can use something that has been utilized for a relatively long time. And then on top of that, if we just take a look more at the East Coast in general, there's a lot of different projects that are already being bid and developed here, as a lot of people talked about. And we also have these different targets that are being set. So the Biden administration is looking for 30 gigawatts by 2030. New York State is looking for 9 gigawatts by 2035. And a lot of these states all up and down the East Coast, they're very interested in, they have goals within the next 15 to 30 years to provide anywhere from 50 to 100% of their power from renewable energy. But something to keep in mind is that if we're being serious about hitting those goals, when we're setting them and putting them out there, that offshore wind is definitely going to need to play a very large role in that. Traditional renewables such as onshore wind or onshore solar are not as feasible when you're talking about some of these areas. There's either not the land footprint to build them or the resources for things like solar in the Northeast. It's really not there to get the energy density you need to actually start hitting some of these numbers that we're discussing here. And then finally, that just brings me to some of the opportunities in offshore wind and where you guys can all get involved. So I'm breaking this down into 4 main sections. The first is basically your design, then development, construction, and operations. So starting with design, we need people, especially engineers, to design all the different components everyone's been talking about. We need someone to design the turbine. We then need someone to design the foundation that the turbine's actually going to connect into. Then we need designers for the substations themselves and the cables. The types of classes that would be relevant to take and that and the type of areas of expertise that the OEMs have are listed here, and you can really see that if you are interested in any specific area and you want to become a subject matter expert in that, there is a place for you to go. Every single one of these has their own departments within the OEMs and the turbine designers, and same with the foundations and substations. So there's really a wide breadth of engineering areas for you to get involved in the design side. The design is only really one part of the wind farm. The next thing that you would get into is the development, which is, okay, I have these turbines I can use, I have these foundations I can use in the substation, which combination of them am I going to use, and where am I going to put them? And in the development, that's where you would get a lot into things like data analytics and numerical methods, as well as statistics, because you have to know, okay, what is the expected wind distribution in this area? How much energy can I expect to get if I build it here? You then need to look into things like meteorological and oceanic studies, again, to know some of your wind and weather conditions, but also, what is my sea state going to be in this area that I built? How often do we think we're going to be able to actually access the turbines? Things like that. And finally, if all that other stuff checks out, what is the civil engineering looking like? Is the foundations actually capable of being put in this area? Or is there going to be rock removal that we need to do? Is it still feasible to build in this area if we need to do that rock removal? Those types of things. Once you decide where you want to build it, then you need to go into wind farm construction. And this is where things like marine sciences, environmental studies, and it's really involved in both the development and construction also become really key, because at this point you need to make sure that you're building the project in a way that is taking into account the ecological impact and also the impacts to the environment, because all the projects you are trying to show that there's obviously a net benefit here, but you need to keep in mind, is there any migratory species that are going to be in this given area? Am I going to be involved when the vessels are going in and out through a whale migratory path? Things like that. And all very critical to be thinking about in these phases of the project. And then finally, from the engineering side, rigging, lifting, any statics or strengths classes becomes very relevant here. And again, all these ships are going to have people who are well versed in this, and someone who can check the lifting plans and make sure, hey, we're good to go do this thing. And then finally, for wind farm operations, which is where I work in, pretty much everything that I talked about above is also relevant there. But specifically in my day-to-day, a lot of focus on controls, probably followed by data analytics, strength materials, especially on different bolted joint assemblies, because there's a lot of those in the wind turbines, and then vibrations are probably some of the biggest things I'm involved with. But again, as I mentioned, pretty much everything above, you're operating the asset that was designed, so you still need to have the same areas of expertise and the same people to know. And then what I want to just close with is two final points, which is when you're considering your career, whether it's in offshore wind or elsewhere, keep in mind the types of paths that you can have. One is to have become a subject matter expert where you don't maybe narrow but deep on a specific area. You are the vibrations person, or you're the composite designer and you're working on that blade design. Maybe you're focused just on that. Or there's also abilities to be a generalist where you weave together multiple different areas of knowledge, and maybe you're more of a systems designer where, okay, the blades team designed this blade, but then you're working with the pitch bearing team, the hydraulics team to make sure, hey, we can actually put this together to have a functioning turbine. Either way can be extremely fulfilling, but it's just a different thing for you to think about as you're trying to get involved in the industry. And then the other thing I just want to mention is the opportunities for improvement within the offshore wind industry are vast. I want to really emphasize that this is not an optimized industry yet, and that as a young engineer getting into it, it's honestly something that is very entertaining and fulfilling to work in because you have the ability to make actionable impacts from day one. If you compare that to something like commercial aviation or whatnot, there's still opportunities to work and maybe improve things, but again, that's already been very much optimized. But you saw from my earlier slides, we went from a 1.5 megawatt turbine 15 years ago to an 11 megawatt turbine. Now, things have not yet been optimized. There's a lot of low-hanging fruit. There's a lot of ways that, by us getting involved now, we can improve things for the future. And with that, I think that pretty much covers everything I had to say, but I'm open for any questions.